Welcome back. So we're going to pick up where we left off and now talk about residuals and residual plots. So to recall that the least squares regression process is the method of deriving the best fit line that minimizes the vertical distance, the y distance between the data point and the resulting line. And of course, no data, usually real life data at least, doesn't fall exactly on a straight line. It's going to be scattered about a line. So we have a little bit of error left over. And that error is what we call a residual. So a residual is the difference between what we actually observed in our data point, the actual point, and the vertical distance to our regression line. So in the picture that's used in your textbook, you'll see these vertical distances, right, shown like here, right, from the point, the vertical distance, the y distance from the point to the line, to the least squares regression line, which is shown here in green. And the residual is what we actually observe, the actual observed y value, less what our model predicts, what our equation predicts, and that's the predicted y value. And when the line is being derived, what the calculator is doing, or the computer is doing behind the scenes, is it's finding the equation that minimizes the sum of the squared residuals. So the vertical distance is the residual itself. If I were to square it, what this picture is trying to show is literally making a square. So r squared would be the equivalent of the area of that square. If I add up all the different areas of all the squares, that sum of the area of the squares would be the smallest using this best fit line compared to the sum of squares using any other best fit line. So now let's continue with our example that we were working with earlier when we derived the equation of the regression line for this set of data. And so if you recall, we have a set of students who recorded the time that they spent studying for an exam and then the resulting score on the exam. And we plotted this data, we graphed it, we put it into our graphing calculator, and we derived the least square regression equation. So after putting the data in our calculator, we were able to get our regression equation here. The predicted exam score is equal to our y-intercept plus the slope times the amount of time studying in hours. And we plotted our data, we got our scatter plot, and so now what we need to do is calculate the residuals and find our residual plot. And you'll notice that on the least square regression line, where we have the least square regression line here is shown on our scatter plot, when we have the actual observed data points that lie above that line, we would get a positive residual. When we have a point that lies below the line, we would end up with a negative residual. So you might be asked, does the model overpredict or underpredict what would be typical? So if you have a point like this one, let's see if, like this one right here, that's above the line, the points above the line, so our model is under predicting the person's score at that given X value, which would be about right here, right? Like a little more than 2 hours, right there somewhere. If we picked a different point where the observed value is below our regression line, our model would be over predicting somebody's score based on that X value that's given. So that's kind of important to understand. And then what we're trying to do now is use our calculator to derive this residual plot over here. So now what we want to do is create our residual plot in our calculator. So I already have all of the data entered here in list 1 and list 2, like I had before. And what I want to do is go ahead and display my graph of the residuals. So what I've already done, I've clicked on Stat, and I've gone to Calculate, and I went to number 8 to get to my linear regression. And I stored my equation in Y1, and I click on Calculate. So I've run the regression already. So I've done the regression. Once I've done that, now I can go to Stat, change my stat plot, go to second Y equals, hit Enter, and I'm going to leave my graph a scatter plot. It's still a scatter plot, but what I'm graphing changes. So I want to leave my X list as L1, list 1. My Y list, I'm going to change to residuals. So I'm plotting my X values against my residuals. So I'm going to click on second stat, second list, right above that. And then notice that down here for number 7, it gives me the option to put in residuals. So I'm going to click on that. And here in my graphing setup now, you see that it'll be the X list is list 1, Y list is residuals. When I graph this, it's going to show up like what happened to my data. Nothing's there. All I have is the line. Well, this line doesn't really mean anything anymore because that's still what is in my Y equals from doing the regression. And what I'm interested in is the residual plot. So if I click on Graph, go to Zoom, and then 9, Zoom Stat, then I will see this crazy assortment of points here. So what this is showing, these are my actual data points. So these are my X values. My X values, remember, didn't change, but now the Y values are actually the residuals. So it's the vertical distance to the least square regression line. So you want to think of this X-axis. It's like we took the regression equation that was sloped and we just flattened it out. And now these residuals are just measuring the vertical distance to that line. The neat thing about it is this is where the trace function really comes in handy, because if I'm asked to find the residual for one of my data points, I can just click Trace and use my arrow key and look at the X value down here at the bottom to follow along, and you'll see how this X value, that's X equals 3, that's a negative residual because this is below the regression line. So my model, my regression equation would over-predict this person's score. And so I get a negative residual, negative 2.3 and something. If I get to a different value, tracing along here, there. So if I get to hours studied is just 3/4 of an hour, this is a positive residual. So my residual here is 5.899. And again, remember the way you calculate this, you have the observed value of Y, what we actually observed, what their test score actually was, compared to what our model would predict that score to be at that same X value. The purpose of a residual plot is to help us assess whether or not a linear model is the best fit for our data. So if a linear model is a good fit for our data, several things will be true. First of all, we will have graphed the scatter plot originally, and it will show a somewhat linear pattern. Secondly, the correlation coefficient R will be fairly strong, so ideally more than, say, 0.7, 0.75. And the R squared value would be strong, so the linear model predicts a high percentage of the Y values correctly. But lastly, we need to look at our residual plot. And so our residual plot needs to be scattered. There can't be any kind of definite pattern such that all the points are way above the line or all the points would be way below the line. In this case, for a small set of data, this would be considered a fairly scattered pattern. And so it shows us, it gives justification that a linear model is actually a good fit for our data. The last thing we're asked to do is find the residual for Nancy's score. So first thing I have to do is go back and say, well, what was Nancy's score? So Nancy, if I go back to my original table, she spent 4 hours on her studying, and so I can trace this along to find my x value of 4. Since there's only one x value of 4, it's pretty easy to know that this happens to be Nancy's score. So if I'm using my graph, I can use the trace function. It will tell me the residual right here, negative 3.093. I can also do this a couple different ways. I can go back to my list, and in my list 3, I'm going to scroll to the right and go up to highlight list 3. Now that I've already run my regression, I can put the residuals for the list in list 3, which can be really helpful. So I'm just going to click on second list, again pick number 7, and what that does is it will populate the residuals for each of my data points right here. So this would be Nancy's point. She studied 4 hours, she scored an 83 on the exam, and then we calculate her residual would be negative 3.093. Now, if I don't have all the data points, what I would do is go back to my actual equation, and remember I've saved my equation in my y equals my y1. So another way to do this would be, say, alpha F1, and I'm going to put in the value of 4, which is the x value for Nancy's point, and hit enter. So my model, our regression equation, our line, if I plug in 4 for x, then my equation will give me 86.09. So my model predicts that a person who studies 4 hours would earn a score of 86. Nancy didn't do that. Nancy didn't score as well as that. So the model actually over predicts her score by a residual of about negative 3. So it's over predicting her score by about 3 points. So when we're answering a question that's asking us to calculate the residual, we definitely need to show work on how we're getting the numbers, not just plug them into your calculator. So on your paper, you would need to show the predicted exam score and plug the value into the equation. So I'm using Nancy's score, so I'm getting Nancy's values right here. And so I go back to the original table, I get x equals 4, and I know that my y value, her exam score in this case, was an 83. So first I want to plug in what is Nancy's predicted score. So just plug 4 in for x and to get my y. So I get my y value is, my predicted exam score is 86.093, and then use that to calculate the residual. So I have her actual score minus the predicted score gives me negative 3.093. So then you just need to make sure that you interpret that. So what does that mean? It just means if we had used our model to predict Nancy's score, the model would have predicted her to score about 3 points higher than she actually did. So the last thing we want to talk about fairly quickly are the impact of outliers and influential points. And so remember that an outlier is usually a point that is outside the general pattern, but it's in the y direction. It's still within the x values, in the range of the x values, but it might stand out in the vertical distance. An influential point typically is outside of your normal x values or outside the rest of the pack of your x values. An influential point is called that because it has a really strong influence on the regression line itself. And so if you have an influential point, if you add it or subtract it from your data set, you'll see a bigger impact to your r and r squared and your y-intercept. So let's look at these two different situations with Sebastian and Kylie, and we'll add those to our data set and see what happens. So in our first situation, we're going to add Sebastian here to our data set. So Sebastian studied for 2 hours and he scored a 40 on the exam, poor Sebastian. So we're going to add this value to our original data set and then go and plot the data. So I'm also going to go ahead and do the linear regression in my calculator on our new data set. So on the left over here, we have the original data set, and on the right, we have our added point with Sebastian in here. And the point is circled down here in yellow. So if you look at this, you'll notice you want to look at a couple of things. First of all, look at your least square regression line and where that hits your y-intercept. So you'll notice the y-intercept here versus here. And again, I can look at that in my regression output. Just look at my A and see, is it a big difference or not a big difference? So the y-intercept, when we added Sebastian, it did move that, that y-intercept down a little bit. The slope of the line, does it look that different? Not too much, right? So the slope increased slightly when we added his point, but it just went from 6.77 roughly to 6.94. So not a huge influence on the slope. And then the R and the R squared, there is somewhat of an impact on R. So R, remember, that means how correlated, how tightly clustered are these points around the regression line. So when I add Sebastian's point here, that's highlighted in yellow, obviously he has a bigger vertical distance from the regression line. And so that's a fairly large residual, if you want to think about it like that. So it's a very large residual in terms of this vertical distance here. That would be my residual. And so outliers tend to have large residuals and less of an impact on the regression line itself. So let's compare Sebastian to if we add Kylie's data. Okay, so now I went and I took Sebastian's data back out. I'm starting again with my original data set that we started with, and I'm going to add Kylie's information. So Kylie, poor Kylie, studied for 7 hours for this test, and she scored a 65. Now, did she really study all 7 hours? I don't know. But regardless, that's her data. So she scored a 65, having put in 7 hours of work. So now her data point is over here highlighted in yellow, and you'll see that that's the furthest out with my X values. So it's outside of the X values that I already have in my data set. It's also outside of my Y values. And so that point is going to be very influential in terms of my overall data set. So let's look at the impact to what's going on here. So my y-intercept, let's see, my y-intercept went from 59 to 65. So that changed more significantly, right? And then what happened to the slope? Well, with an influential point, the slope tends to be pulled toward, that regression line gets pulled toward the point. So look what happened to the slope. I went from 6.77 roughly to a slope of much less steep, much flatter, 3.26. So that regression line flattened out. And then the R squared value, now I dropped from 75% to only 28% now of all the variation in Y is now explained by my least square regression line. The R value, the correlation, also dropped. Now, with influential points, sometimes that correlation goes up. You have to be careful with that one, because the more extreme the distance is from my new influential point, the further outside it is from the rest of the X values. If it's a really far out X value, then I could have a situation where the R value, the correlation, actually goes up, because now I have a group of points that don't look very linear, but then I add this point way out here that makes it look very linear. So you have to be a little bit careful with R, but notice how influential Kylie's data is to our overall line. So you want to note all the changes and the impact of adding Kylie's data to our data set. So let's go back and look at Margaret. So Margaret was part of our original data set. We kind of noticed at the beginning that she was a somewhat stood out from the pack. So Margaret is right here. And so is her data influential? Like, you hate that person in the class who ruins the curve, right? They studied too much and they scored really well, and everybody else is clustered around a certain value, but this one person got like an A+ on the test. That's Margaret, right? So she studied for 6 hours and scored a 96 on her test. Well, what would happen if we took her out of the mix? So let's take her out of the mix, and so that's what we're doing here. So we're taking Margaret out. Notice that the pattern, as you're just looking at the data itself, the pattern appears to be a little bit more spread out, like the points aren't as clustered around that line, and it's not looking quite as linear. So especially if I had changed the window settings on that graph without Margaret to just go up to x = 4 or x = 5, it might have given an even different view. It might have made them look even more spread out. So be careful about that. But taking Margaret out of the mix definitely drops our correlation value. It also drops the R² value. It adjusts the y-intercept slightly, not too much. And the reason is when we have Margaret here, this point, right? Sorry, I didn't do a very good job drawing that. But when we have Margaret's point there, Margaret is still in line relatively with the x values and the y values. So this is a situation where she is, her data point might be an outlier in the x range of values and in the y range of values, but not really as not really when taken together as a coordinate point, because her x-y coordinate pair follows that line very closely. And notice what a small residual this is right here. This vertical distance from Margaret's data point to the least square regression line is very small, because her point is influencing that line, and it's really kind of acting like a magnet. It's pulling that line right toward her. So without Margaret's data in there, the data appears to be less clustered and less linear. So just some things to look out for, and hope that that was helpful for you guys. The last thing we'll talk about in our next video is computer output, and you want to know how to read computer output given that information, and then write your equation of your least square regression line from that. So have a wonderful day, and we'll see you next time. Bye-bye.